On August 10th, 1628, the most heavily armed warship in the world sailed about 1,000 meters into its maiden voyage, caught a small gust of wind, and immediately fell over and sank. In 32 meters of water, in Stockholm harbor, in front of the king. The ship was called the Vasa. It had cost more than the entire annual budget of the Swedish Navy. It killed about 30 people, although the exact number is still debated. And the reason it sank, the reason that ship was always going to sink, comes down to a single number. A number nobody on board had ever heard of. A number that, in 1628, did not yet exist as a formal concept. This is the equation that killed a ship. Sweden in the 1620s is at war. Specifically, it is in the middle of the Polish-Swedish War, part of a longer chain of conflicts that will eventually pull Sweden into the 30 Years' War on the Protestant side. The king is Gustavus Adolphus, Gustav II Adolf, a man who will, before his death, be called the Lion of the North and the father of modern combined arms warfare. He is also, in 1625, an impatient client of his own shipyards. In January 1625, the king signs a contract with a Dutch master shipwright named Henrik Hubertson. Sweden needs warships. Hubertson is to build 4. The 2 largest are intended to carry 72 cannons each, a staggering armament for the period. At the same time, in another part of the world, the Swedish fleet loses 10 ships in a storm. The king's pressure on the shipyard intensifies. Here is a detail you have to understand about 17th century shipbuilding. There were no blueprints. Not in the modern sense. The shipwright carried the design in his head, in the proportions of certain reference measurements, the length of the keel, the breadth of the beam, the depth of the hold. A skilled master could build a ship that floated and sailed well, using rules of thumb refined over generations. But rules of thumb is exactly the right phrase. There was no calculation of stability. There was no equation that told you, in advance, whether a particular hull at a particular load would stand up in the water or fall over. In late 1625, Hubertson lays down the keel of the largest of the 4 ships. At some point during construction, and the exact decision point is still debated by historians, the king demands that the ship be built larger than originally planned. More guns, a second gun deck, 2 full decks of heavy cannon. In 1626, Hubertson falls ill. He dies in 1627. His brother Arendt and his second-in-command take over construction. The ship is finished in the summer of 1628. Nobody has done a sea trial. Nobody has even done a stability test in the modern sense. But somebody, a vice admiral named Claes Fleming, the captain of the Stockholm fleet, does in fact conduct what amounts to the first stability test in the history of shipbuilding. The test is extraordinary, and it is documented in the official inquiry that followed the disaster. In the days before the maiden voyage, with the ship moored alongside the royal palace, Vice Admiral Fleming has 30 sailors run back and forth across the upper deck, from one rail to the other, as fast as they can, as many times as they can. This is, in 17th century terms, a stability test. The idea is to see how the ship rolls when significant moving weight crosses her beam. After 3 passes, Fleming stops the test. The ship has rolled so dramatically that he is afraid she will capsize at the dock. He turns to the officers around him and says, and this is recorded testimony, that he wishes the king were home, because if the king were home, the ship would not sail. The king is not home. The king is at war in Poland. The king has written letters demanding the ship sail as soon as possible. The test is, in essence, ignored. Or rather, and this is the more honest reading, the test is observed, its results are understood, and the political cost of acting on those results is judged to be higher than the engineering risk of ignoring them. On August 10th, 1628, the Vasa set sail. The weather is described as fine. There is a light breeze from the southwest. The lower gun ports are open because the gunners are firing a salute. The ship moves about 1,300 meters from her mooring before she encounters her first real gust. She heels to port. She rights herself slightly. A second, slightly stronger gust hits her. She heels to port again, and this time she does not come back. Water pours into the open lower gun ports. The ship continues to roll. Within minutes, she is on her side, then upside down, sinking by the stern in 32 meters of water. So now we have to ask the question, why did a ship that floated peacefully at the dock, that obviously displaced more water than her weight, fall over in a light breeze? The intuitive answer is that she was top-heavy. That answer is correct, but it does not explain anything. Lots of ships are top-heavy and float fine. The cruise ships in the harbor of any major port today are wildly top-heavy by 1628 standards. The question is why this particular top-heaviness was fatal. Here is the central insight, and it is one of the most beautiful and counterintuitive results in basic naval architecture. A floating object has two centers that matter. First, the center of gravity, the point at which you can imagine all of the object's weight concentrated. Second, the center of buoyancy, the point at which you can imagine all of the upward force of the displaced water concentrated. For an object to float at all, those two forces have to be equal in magnitude: gravity pulling down, buoyancy pushing up. But for the object to float stably, the relationship between those 2 points has to obey a particular geometric condition, a condition we now call metacentric stability. Now imagine the hull tips slightly. Say a gust of wind pushes it a few degrees to one side. The center of gravity stays in roughly the same place inside the hull. It doesn't move with the tilt because the cargo and ballast and crew haven't moved relative to the ship. But the center of buoyancy, that does shift. Why? Because the shape of the hull that is now underwater has changed. More of one side is submerged. The center of buoyancy moves toward the submerged side. And this is where the magic happens. If the center of buoyancy moves far enough to the submerged side, the upward force of buoyancy and the downward force of gravity now act along different vertical lines, and those two forces create a torque, a righting torque. They twist the ship back upright. But, and here is the killing condition, the center of buoyancy only shifts enough to create a righting torque if the hull's underwater shape is wide enough relative to where the center of gravity sits. If the center of gravity is too high, the geometry breaks down. When the hull tips, the center of buoyancy still moves, yes, but not far enough. The two forces now act along vertical lines that pass on the same side of each other, and instead of a righting torque, they create a capsizing torque. The ship rolls further, and further, and further, until water comes in through the gun ports and the math becomes terminal. To formalize this, naval architects use a concept called the metacenter. The metacenter is a slightly strange geometric construction. Imagine you draw a vertical line straight up from the center of buoyancy when the ship is upright. Now tilt the ship a small amount. The center of buoyancy moves to one side, and from this new position, you draw a new vertical line straight up. Those two lines, the original upright vertical and the tilted vertical, intersect at a point inside or above the ship. That intersection point is the metacenter. It is labeled M. Now, the killing question is simply this. Is the metacenter above the center of gravity or below it? If the metacenter sits above the center of gravity, the ship is stable. When she tilts, she rights herself. If the metacenter sits below the center of gravity, the ship is unstable. When she tilts, she keeps going. The vertical distance between the metacenter and the center of gravity is called the metacentric height, usually written as gm. When gm is positive, meaning m is above g, the ship is stable. When gm is negative, the ship is doomed. For a well-designed warship of the Vasa's general type, modern naval architects estimate that a healthy GM is on the order of a meter, sometimes more. When the Vasa was reconstructed and analyzed after her recovery in the 20th century, naval architects calculated that her GM at the moment she sailed was somewhere on the order of 0.3 meters or less. Some analyses place her effective GM in certain loading configurations at essentially 0. In a few degrees of heel, with gun ports below the waterline, she may have crossed into negative GM territory. The arithmetic is unforgiving. The Vasa was approximately 69 meters long overall, with a beam of about 11.7 meters. For a ship of that length, that beam is narrow. The hull was tall, 2 full decks of cannon plus an upper deck plus a high stern castle. The ballast in the bilge when she sailed was approximately 120 tons of stone. Modern naval architects have estimated that, to stabilize her properly, she would have needed roughly twice that, maybe more. But the lower gun deck was already so close to the waterline that adding more ballast would have submerged her gun ports, even in still water. She was, in a precise engineering sense, an impossible design. So let's actually write down the equation that killed the Vasa. The metacentric height GM is given by a beautifully clean formula. GM equals KB plus BM minus KG, where K is the keel, the reference point at the bottom of the ship. KB is the height of the center of buoyancy above the keel. KG is the height of the center of gravity above the keel. And BM, the most interesting term, is the distance from the center of buoyancy up to the metacenter. BM is given by an even more striking expression. BM equals I divided by V, where V is the volume of water displaced by the hull. The more water you displace, the more buoyant force you have. And I, this is the magic term, is the second moment of area of the waterline plane. In plain English, I measures how wide the hull is at the waterline, weighted by how far from the center line each part of that waterline cross-section sits. A wide, flat-bottomed hull has a huge I. A narrow, deep hull has a tiny I. So when you put it all together, the metacentric height GM depends on 3 things. 1. How high the center of buoyancy sits. 2. How wide the waterline is, which controls BM. 3. How high the center of gravity sits, which is determined by where you put the weight. To make GM big and positive, you want a wide waterline, big I, a deep displacement, big V, but this term is in the denominator of BM, which complicates things, and a low center of gravity, small kg. The Vasa had a narrow waterline. She had a high center of gravity. Her I was modest, and her kg was huge. The formula does not care about politics. The formula does not care about the king's deadline. The formula returned a number close to 0. And the ship fell over. Now here is the part of the story that I find genuinely poetic. When the Vasa sank in 1628, the equation I just showed you did not exist. The concept of the center of buoyancy was understood in principle from Archimedes, 3rd century BCE. But the formal theory of the metacenter and the GM stability criterion was not developed until the 18th century. The breakthrough is generally credited to the French scientist Pierre Bouguer, who published his Traité du navire in 1746. More than 100 years after the Vasa sank. Bouguer was a hydrographer and mathematician working at a moment when European navies were under enormous pressure to design larger and larger ships. He realized, sitting with the geometry, that the question of stability could be reduced to the position of a single virtual point, the metacenter, which depended only on the shape of the hull at the waterline and the volume of displacement. His insight was, in a real sense, the founding equation of naval architecture as a science. After Bouguer, ship designers could calculate in advance whether a ship would float upright. They no longer had to run 30 sailors across the deck and watch what happened. Think about that for a moment. Between 1628 and 1746, navies around the world built thousands of warships, by eye and by tradition, with no formal stability theory. Some of those ships were superb. Some of them, like the Vasa, sank for reasons their builders could not articulate. The math existed, in a sense, in the rules of thumb that good shipwrights passed down, proportions that produced wide enough waterlines and low enough centers of gravity to keep ships upright. But it took 118 years of post-Vasa engineering before someone wrote down the equation that explained why the rules of thumb worked. That delay between disaster and theory is one of the great patterns in the history of science. The catastrophe usually arrives first. The Vasa, having sunk in 32 meters of brackish, low-oxygen water in Stockholm harbor, did something that no other large warship of her era did. She survived. The Baltic Sea has very low salinity, and Stockholm harbor in particular is poor in the shipworms, Teredo navalis, that would normally have devoured the oak of a wreck in tropical or even Atlantic waters. The Vasa sat on the seabed for 333 years, almost completely intact. In 1956, an amateur archaeologist named Anders Franzén relocated the wreck. In 1961, a Swedish naval engineering effort, using cables and pontoons in an extraordinary salvage operation, lifted the Vasa off the harbor floor and floated her into a dry dock. The ship that emerged was approximately 95% original oak. She is, by a wide margin, the most complete surviving warship of the 17th century. She is, today, the centerpiece of the Vasa Museum on Djurgården in Stockholm, one of the most visited museums in Scandinavia. When modern naval architects analyzed the recovered ship, They confirmed in detail what Vice Admiral Fleming's running sailors had already shown in 1628. Her hull form was too narrow for her armament. Her center of gravity was too high. Her ballast was inadequate. Her gun ports were too close to the waterline. In the strict mathematical sense, she was a ship that should not have been built, or, more precisely, a ship whose final dimensions, set in motion by political pressure halfway through construction, took her past the threshold where any rule of thumb could save her. The Vasa is now, in engineering and management education worldwide, a case study. She is taught in business schools as an example of scope creep, a project whose specifications kept growing past the point of structural viability. She is taught in naval architecture programs as the canonical example of metacentric instability. She is taught in organizational behavior courses as a case of testing the finding versus testing the system, a moment when a critical empirical signal was generated, observed, recorded, and then deliberately ignored because the political cost of acting on it was perceived to be too high. All of these readings are true. What I find most interesting, though, is that they all converge on the same point. The math of the world does not negotiate. The metacentric height of a hull is a fixed geometric property at any given loading. You cannot vote on it. You cannot delay it. You cannot make it bigger by issuing a royal decree. When the gust hits, the equation runs in real time, and either you have built a ship that will stand up, or you have built a ship that will fall over. The thing that turned this particular disaster into one of the founding stories of modern engineering is that when the ship fell over, somebody, over the next century, sat down and worked out why. And once they wrote down the equation, no one else had to learn the Vasa's lesson, the Vasa's way. I want to leave you with one thought, and it is the reason I love this story. The metacentric height equation is not, in the grand scheme of mathematics, a difficult one. A modern engineering undergraduate works through the derivation in an afternoon. The components, Archimedes' principle, the geometry of buoyancy, the second moment of area, the idea of a virtual intersection point, were all knowable in 1628, in principle. What was not yet present was the insistence on writing them down in that combination. The naval architects of 1628 did not lack the intelligence to derive GM. They lacked the institutional habit of treating ship design as a thing one calculates before one builds. That habit had to be invented. And the cost of inventing it across the 17th and 18th centuries was a number of capsized ships that history has mostly forgotten, except for one. The Vasa survives because the Baltic preserved her. She teaches because the math finally caught up with her. Strange equations sometimes arrive late. The world runs them on schedule anyway. If you enjoyed this one, the Vasa's sister ship, the Äpplet, identified on the Baltic floor in 2021, is a story for another day. Strange Equations is here for the math behind the moments that nobody at the time was calculating. If that is your kind of channel, subscribe. Thank you for watching.